Hi all, how is it going? So, if you are used to real numbers, we are used to functions that bounce back and forth everywhere and they are super smooth like the sine or the cosine and they never go to infinity. So they are really bounded, they're really perfectly inside. But something really weird happens in the complex world. Indeed, all of this becomes impossible. The complex plane is incredibly rigid, and I'm going to show you why it is and why it's so beautiful and so important the complex plane is so rigid. Today, we're going to look it up at Liouville's theorem and all the magic behind it. Let's state Liouville's theorem simply. If a function is analytic and bounded on the whole complex plane, then it must be constant. Let's break it down. Analytic means that the function is holomorphic, which means complex differentiable, everywhere in the complex plane. Bounded means that there exists some constant m bigger than 0, such that the modulus of f of z is less than m on the whole complex plane. Look, here's a complex analytic function trying to wiggle and stay bounded, but there is no chance for her. For Liouville's theorem, it's gonna always be bounded. This is really surprising, because for instance, in the real world, this doesn't apply. Look at the sine of x, for example. It wiggles everywhere in the plane, is bounded, and is perfectly smooth. So Liouville's theorem does not apply. There is something deeper in the complex plane that makes its geometry really, really rigid. But why do we care about this theorem? Well, one of the applications is that now, from the singularity of a function and its behavior at infinity, we can actually characterize the function itself. And this is really powerful because in real-life application, this happens a lot of times. Let's see how we do it. So, let's see our theorem in action. As the first exercise, I want you to consider f of z to be analytic in the whole complex plane except at the point z0 equal to 0. And furthermore, we're going to assume that the limit as f of z goes to infinity is equal to 0, okay, it's going to be crucial, and also that f of z minus 1 over z is analytic everywhere in the complex plane. And our objective is to find this function f of z. So as I just said, Liouville's theorem is important because it allows us to find f of z in exactly this situation, meaning that we have the behavior of the function at infinity and the behavior nearby a singularity, then we can find the function f of z itself. So how do you do it? Well, first let's consider another function, g of z, to be equal exactly to f of z minus 1 over z. Thanks to our second hypothesis, we know that this function is analytic everywhere. Furthermore, we know that the limit as z goes to infinity of g of z is equal to the limit as f of z goes to infinity minus the limit of 1 over z as z goes to infinity. But now f of z goes to 0 for the first hypothesis, and 1 over z goes to 0 too. So the limit of g of z as z goes to infinity is exactly equal to 0. What does it mean this? It means that eventually my function would be bounded by a constant at infinity, which means in particular that there exists a constant m bigger than 0, such that the modulus of g of z has to be less than m. And why is that? Because again, the limit as g goes to infinity is equal to 0. So after sometimes in the complex plane, that we can draw it here, outside a really, really, really big circle, the function outside is going to be small, and the modulus is going to be small too. And inside here, we can use Heine-Borel theorem to conclude that the modulus of my function has to be bounded. Therefore, I know that this constant exists, so I know that the modulus of g of z has to be bounded by something. Well, now I know that by Liouville's theorem, g of z has to be a constant. So g of z is equal to a constant c. Okay, that's great. And now what is this constant? Well, now the left-hand side depends on z, but the right-hand side does not depend on z. So what can I do? Well, I can compute the limit on both sides at z goes to infinity. So I can compute the limit at z goes to infinity of my g of z, and this one has to be equal to the limit as z goes to infinity of my constant c. And now the left-hand side, from before, I know it's going to go to 0, and the right-hand side instead is a constant, so it's going to be always equal to the same things. So this implies that 0 is equal to my constant c. So the constant has to be equal to 0. Okay, so what we prove up until now is that g of z is equal to 0, identically dead equal to 0. But what's the definition of g for us? Well, g is equal to f of z minus 1 over z. So this implies that f of z minus 1 over z has to be equal to 0, which means that f of z has to be dead equal to 1 over z. So from the singularity behavior of my function, so the behavior by not the singular points, and its behavior at infinity, I can extract the function itself using Liouville's theorem. And that's why this theorem is so important. Let's look at another example. In this case, we want to find f of z, knowing that f of z is analytic everywhere except the points at 0 equal to 1. The limit of f of z minus z squared minus z is equal to 0 as z goes to infinity. And that f of z minus 3 over z minus 1 is analytic everywhere. So it's a bit different from before, but you can see some similarity. Now, what's the idea to find f of z? Well, I'm going to consider again the function g of z to be equal now to f of z, okay, this is not surprising, minus 3 over z minus 1, which is the complete analog of before. But now I'm going to also consider this extra part that I didn't have before. So I'm going to also subtract z squared minus z. And it's going to be clear in a second why I do that. So I pick f, I subtract the singular part, so this singular part here, and also I subtract the behavior at infinity, basically, of my function. Okay, the analytic behavior at infinity. And why I do this? Well, because now, what can I do? As before, I can consider the limit as z goes to infinity of g of z. And now this one is equal to the limit as z goes to infinity of f of z minus z squared minus z plus the limit as z goes to infinity of negative 3 over z minus 1. Right? And now, from the first hypothesis, I know that this first limit is going to 0, and the second one I can compute explicitly, which is 0. Which means that once again, the limit as z goes to infinity of g of z is equal to 0. Okay? So we are exactly in the same situation as before, basically. Furthermore, since I know that f of z minus 3 over z minus 1 is analytic everywhere, also z is going to be analytic everywhere, because I have an analytic function everywhere and a polynomial, which is analytic everywhere by definition. Okay, so now, as before, I know that all of this implies that the modulus of g of z has to be bounded by some constant m everywhere. And again, by Liouville's theorem, this tells me that g of z has to be equal to a constant, and reasoning exactly as we did before, this implies that g of z has to be exactly equal to 0, actually. And this is what it tells us. Well, g of z for us was f of z minus 3 over z minus 1 minus z squared minus z and it has to be equal to 0, which implies that f of z has to be equal to 3 over z minus 1 plus z squared plus z. And it looks like witchcraft, but it's only Liouville's theorem at its best. Another slightly more funky application of Liouville's theorem is the following one. So I'm going to assume now that f of z is analytic everywhere, and that its real part is bounded for all z. Okay, so there is a constant m such that the modulus of the real part is bounded from above. Then I want to prove that f of z is a constant. So how do you do that? So first, let's write proof, because this is a proper theorem. So I'm going to consider the function g of z now equal to the exponential of f of z. And this, guys, is a kind of general trick. Whenever you have information about the real or the imaginary part of your function, then considering the exponential solves you a lot of problems. And why is that? Well, because now what you can do, you can consider the modulus of your g of z. So the modulus of g of z, and this is equal to e to the real part of f of z. Okay, so that's it. There is nothing else there. So now what I know that the real part of f of z now is uniformly bounded in all the complex plane. This implies that this is less than equal than e to the m. So this tells us that the modulus of g of z is bounded by a constant. Okay? So this implies, by Liouville's theorem, that there is a constant c such that the g of z is equal to this constant. But now g of z, what it is just e to the f of z equal to c. Oh, so I can just apply the logarithm on both sides and deduce that f of z is equal to the log of c, when this logarithm is the appropriate branch cut of the log, which implies that f of z is a constant. That's great. Okay, so the trick is always, when you have information about the real or the imaginary part, to consider the exponential of that function. So now you can try to prove that if I have the same hypothesis, except that instead of the real part I have the imaginary part, you can conclude the same. Another really important reason why we do care about Liouville's theorem is because it gives us the easiest, most elegant proof of the fundamental theorem of algebra, which is another reason why analysis is just much better than algebra itself. Their most important and fundamental theorem can be proved using complex analysis, and it takes really no time. The theorem states that every non-constant polynomial must have at least one complex root, and we can prove it only in 4 lines using Liouville's theorem. Suppose now that we have a polynomial, p of z, of degree n bigger than 0. And let's pretend it has no roots anywhere in the complex plane. This means that p of z is never equal to 0. If it is never 0, we can define a new function, f of z equal to 1 over p of z, such that it's analytic everywhere, since the denominator does not have any singularity and is always differentiable. So that's great. But now, what happens as z gets bigger and bigger? Well, p of z is going to go to infinity too. Therefore, 1 over p of z is going to go to 0, exactly as in the exercises before. And now, because it's going to go to 0, this means that f of z must be bounded everywhere and never blows up to infinity. Which means that by Liouville's theorem, f of z must be a constant. But now if f of z is a constant, then also p of z has to be a constant. But we assume that p of z is a polynomial which is non-constant, so this is absurd. which means the P of z must have at least one complex root. Let's look at an example. Now you see that for a polynomial of degree 3, for example, we have exactly 3 roots, 1, 2, and 3. So once again, analysis beats algebra, makes everything much easier and smoother. Thanks, Liouville. So the rigidity of the complex plane is what makes it so beautiful, so important, and makes complex analysis such an amazing tool to study everything. Well, I hope you enjoyed the video, thank you for watching, and I'll see you next time. Ciao!